Good evening, Dr. Phil here. Today we'll be discussing on the gas laws, gases and vapors part 2. Boyle's law. At a constant temperature, the volume of a fixed mass of perfect gas is inversely proportional to absolute pressure. P times V equals K, or V is proportional to 1 divided by P. A useful mnemonic: water boils at a constant temperature. Clinical relevance. Boyle's law can be used to calculate the volume of gas remaining in a gas cylinder. At constant T, PV is a constant, so P1 times V1 equals P2 times V2. A size E oxygen cylinder has an internal volume of 10 liters and so contains 10 liters V1 at 13,800 kPa P1. Note that P1 here is absolute pressure, so 100 kPa of atmospheric pressure must be included. At atmospheric pressure, P2 equals 101 kPa. There will therefore be 1,380 liters of oxygen V2 available from the cylinder. Body plethysmography is a method used to measure FRC. The subject sits in an airtight chamber and inhales or exhales to a particular volume. Then a shutter drops across their breathing tube. The subject then makes respiratory effort against a closed shutter. Their chest volume expands and this decompresses the air in their lungs. Chest volume increases, resulting in reduced box volume and increases the pressure in the box. The FRC can be deduced using Boyle's law. Charle's law. At a constant pressure, the volume of a fixed mass of perfect gas varies proportionally to absolute temperature. The relationship between volume and absolute temperature is linear, i.e., at absolute zero, that fixed mass of gas would have no volume. V divided by T equals K, or V is proportional to T. A useful mnemonic: Prince Charles is under constant pressure to be king. Clinical relevance of Charle's law. During pulmonary function testing, a patient exhales gas at body temperature into a spirometer at room temperature. The volume in the spirometer is corrected from ATPS, ambient temperature and pressure, saturated with water vapor, to BTPS, body temperature and pressure, saturated with water vapor, according to Charle's law. Convection. The air around the body is heated by body heat during anesthesia. The volume of the mass of gas increases according to Charle's law and therefore rises away from the patient as gases that are less dense rises. The gas thermometer contains a constant volume of gas in a sealed container. According to Charle's law, as the ambient temperature rises, the volume of the gas will also rise and vice versa. This change in volume is measured, which is directly proportional to the change in temperature. Gay-Lussac's law. At a constant volume, the pressure of a fixed amount of perfect gas varies proportionally to absolute temperature. P divided by T equals K, or P is proportional to T. Clinical relevance. Storage of gases in cylinders. According to Gay-Lussac's law, as the ambient temperature rises, the pressure inside the cylinder will also rise. For nitrous oxide, the critical temperature of nitrous oxide is 36.5 degrees Celsius, so under normal circumstances, in temperate climates, it is stored in a liquid phase with its vapor above it. The filling ratio. The filling ratio is defined as the ratio of the weight of substance in the cylinder to the weight of water the cylinder could contain if fully filled. It is the mass of gas in the cylinder divided by the mass of water that would completely fill the cylinder. This is an issue for nitrous oxide and carbon dioxide because it is stored as a liquid in cylinders. There has to be a gas space at the top of the cylinder. Slight increases in ambient temperature can cause a dramatic increase in cylinder pressure and possible explosion if there is a very small gas space. The filling ratio in the UK is 0.75 to allow for expansion and to limit increases in pressure, and it is even lower in tropical climates 0.67 to avoid dangerous increases in pressure due to higher ambient temperature. Oxygen. Liquid oxygen must be kept at a temperature below its critical temperature of negative 118 degrees Celsius to avoid dangerous pressure buildup. The hydrogen thermometer. This thermometer contains a constant volume of hydrogen in a sealed container. According to Gay-Lussac's law, as the ambient temperature rises, the pressure inside the hydrogen thermometer will also rise and vice versa. This change in pressure is measured, which is directly proportional to the change in temperature. Avogadro's law. Equal volumes of gases at the same temperature and pressure contain the same number of molecules regardless of their chemical nature and physical properties. 1 mole of any gas at standard temperature and pressure occupies 22.4 liters, where STP equals 273.15 Kelvin and 101.325 kPa. Avogadro's number, or Avogadro's constant, is 6.02214076 times 10 to the power of 23, which is equivalent to 1 mole, and the number of atoms in 12 grams of carbon-12. Clinical relevance. Avogadro's law can be used to calibrate a sevoflurane vaporizer. The number of moles equals the mass of substance in grams divided by atomic mass. The molecular weight of sevoflurane is 200. 200 grams of sevoflurane equals 1 mole. 1 mole of sevoflurane occupies 22.4 liters at STP. If a vaporizer contains 40 ml of sevoflurane, which is equivalent to 0.2 moles, this occupies 4.48 liters at standard temperature and pressure. If 40 ml of sevoflurane is vaporized completely into 224 liters of oxygen, the resulting concentration will be 4.48 divided by 224, or 2%. The number of mL of liquid anesthetic agent used by a vaporizer per hour equals 3 times fresh gas flow in liters per minute times volumes %. 1 ml of liquid volatile agent typically yields 200 ml of vapor. Universal gas law. PV equals nRT, where P is absolute pressure, measured in pascals, V is volume, measured in meter cube, N is the number of moles of a gas, measured in moles, R is the universal gas constant, which is 8.314 joules per Kelvin per mole, and T is temperature, measured in kelvins. Combined gas laws. P1 times V1 divided by T1 equals P2 times V2 divided by T2. Clinical relevance of the universal gas law. It can be used to calculate the remaining contents of an oxygen cylinder. Under normal circumstances, T is constant at room temperature, V is constant as the cylinder has a fixed volume, and R is by definition a constant. Therefore, P is proportional to N. Gauge pressure P can thus be used to measure the amount of oxygen remaining in the cylinder, N. The universal gas law can also be used to calculate the remaining contents of a nitrous oxide cylinder. Under most circumstances, nitrous oxide is stored below its critical temperature of 36.4 degrees Celsius. Nitrous oxide therefore exists in the gas cylinder as a vapor in equilibrium with the liquid below it. The total quantity of nitrous oxide contained in a cylinder may be ascertained only by weighing. The cylinder weights, full and empty, are stamped on the shoulder of the gas cylinder. The weight of the empty cylinder, known as the tar weight, is subtracted. By applying the universal gas equation, the remaining volume can be calculated, and by applying the Avogadro's law, the number of moles of nitrous oxide may be calculated. Dalton's law of partial pressures. The pressure exerted by a mixture of gases is the sum of the partial pressures of its constituents. Clinical relevance. The pressure that is exerted by each gas in a mixture of gases is the same as it would exert if it alone occupied the container. Dalton's law explains why the settings on variable bypass vaporizers do not have to be altered when used at higher altitude. Effects of high altitude or hyperbaric conditions on variable bypass vaporizers. The amount of vapor carried by the fresh gas flow is a function of the saturated vapor pressure of the agent and the atmospheric pressure. At high altitude, the SVP of the volatile agent is unchanged. Atmospheric pressure decreases. Actual output of vapor in volumes percent increases. Partial pressure of the volatile agent is unchanged. The vaporizer can be used in the same way at high altitude as at sea level because it is the partial pressure of the agent and not the concentration that is responsible for anesthesia. This also applies to vaporizers used under hyperbaric conditions. For example, at 6,000 meter height, where the barometric pressure is 380 millimeters mercury, which is 50% of sea level barometric pressure, the vapor output doubles. 3% sevofluorine as dialed up will deliver 6%. Be it at 6,000 meters or at sea level, the partial pressure is the same at 22.8 millimeters mercury. Under hyperbaric conditions, the SVP of the volatile agent is unchanged. Atmospheric pressure increases. Actual output of vapor in volumes percent decreases. Partial pressure of the volatile agent is unchanged. The vaporizer can be used in the same way at normal barometric pressures because it is the partial pressure of the agent and not the concentration that is responsible for anesthesia. However, the effects of high altitude on measured flow vaporizers is different than that in variable bypass vaporizers. The TEC6 vaporizer heats desflurane to 39 degrees Celsius to generate a vapor pressure of 200 kPa inside the chamber regardless of what the ambient atmospheric pressure might be. Actual output of vapor in volumes percent will be the same as the dialed up percent regardless of altitude. 10% desflurane as dialed up will deliver 10% at any altitude. An alveolar partial pressure at sea level of 76 mmHg will be halved to 38 mmHg at 6,000 meters. Thus, the dialed up concentration would have to be increased at high altitude to maintain adequate partial pressure for anesthesia. Henry's law states that the amount of gas dissolved in a liquid at a given temperature is proportional to the partial pressure of the gas in equilibrium with the solution. Clinical relevance. Hyperbaric therapy. Delivery of oxygen to tissues has been discussed in a previous video. Kindly refer to that video for further details. As a summary, delivery of oxygen equals cardiac output times arterial oxygen content times 10 measured in mils per minute. Arterial oxygen content equals 1.34 times Hb times SaO2 plus dissolved oxygen 0.003 times PaO2. Dissolved oxygen becomes significant under hyperbaric conditions. The oxygen solubility coefficient equals 0.003 mils per dl per mmHg at atmospheric pressure. Reading air, dissolved oxygen content is around 0.26 mils per dl. Breathing 100% oxygen, dissolved oxygen content is 1.7 mils per dl. At 3 atm in a hyperbaric chamber, breathing 100% oxygen, dissolved oxygen content is 5.7 mils per dl. Dissolved oxygen thus can make a significant contribution to oxygen delivery to the tissues at this level. Decompression sickness. Decompression sickness occurs when rapid pressure reduction causes gas previously dissolved in blood or tissues to form bubbles in blood vessels or tissues. Causes of rapid pressure reduction includes ascending too quickly from a dive, exit from a caisson or hyperbaric chamber, ascent to altitude, etc. Symptoms can be pain, neurologic symptoms, etc. Decompression sickness can be fatal. Gas bubbles causes symptoms by blocking vessels, rupturing or compressing tissue, inducing endothelial damage with extravasation of plasma, and activating clotting and inflammatory cascades. Diagnosis is clinical. Definitive treatment is recompression therapy. Prevention is by proper diving techniques, etc. Relevance to Henry's law. The amount of gas dissolved in a liquid at a given temperature is proportional to the partial pressure of the gas in equilibrium with the solution. The solubility of a gas in a liquid is directly proportional to the pressure exerted on the gas and the liquid. Thus, the amount of inert gases, such as nitrogen and helium, dissolved in the blood and tissues increases at higher pressure. With increased depth, nitrogen in compressed air equilibrates through the alveoli into the blood. Increasing amounts of nitrogen dissolve and accumulate in the lipid component of tissues. Fick's law states that the rate of transfer of a gas through a permeable membrane is proportional to tissue area, A, difference in gas partial pressures on either side of the membrane, P1 minus P2, and diffusion constant D, and the rate of diffusion is inversely proportional to tissue thickness. Rate of diffusion is proportional to A divided by T times D times P1 minus P2. The diffusion constant is proportional to solubility of the gas and inversely proportional to the square root of the molecular weight. Causes of reduced gas diffusion rate in the lungs. Reduced PAA gradient, such as during high altitude or fire combustion. Thickening of the alveolar capillary AC membrane, such as in pulmonary edema and retained secretions. Reduced surface area of AC membrane, such as in emphysema and pulmonary fibrosis. And during reduced time for diffusion, such as during tachycardia. These are my references. Thank you.